Given a sequence, and we would like to add all the numbers together. The sum, if we can define, it's called a series. Right? So given a sequence, so there's a difference between sequence and series. Right? It starts from capital N, could be 5, could be 10. Okay, then how to add them together? You have infinitely many terms here. So this will be defined as a limit, as limit, and this could be, you know, m goes to infinity. If you still use n here, n from capital N to n. So, and this summation means how many terms you have here, capital N, n plus 1, all the way to an. So you have this many terms. The finite many terms you can add them together. If you have infinite many terms, you have to view it as a limit of this and find the sum. Okay, and this is called this is called a series. Okay, called a series. Okay. There are many different types of series because there are many different types of sequences. Okay. The most important one is called the geometric series, okay, which is in the form n start from 0 to, so n can be anything, right? N start from 0 to just AA. Okay, and so the question is whether this one is defined. Okay, it's infinite many sums. Okay, so let's study this. Okay, so this is defined to be the limit, okay, as m approaches infinity. Okay, so how do you see whether the limit exists? Okay. Well, for geometric series, we can add those terms together. The first term is a times r, and a times r to the n. Okay, right? So you have n plus 1 terms, and there's a formula to add them together. You take AR. So those, the geometric series is very special. So it's going to be 1 minus r to the n plus 1 minus r. So don't worry about the denominator. Of course, we have to assume that r is not going to be 1. If r equals 1, you can add all the numbers together quickly. Okay, we just assume r is not going to be 1. All right, so to check whether this sum has a limit as m approaches infinity, you just need to look at r to the n plus 1. Now we have an important fact. Okay, this limit k approaches infinity to k. This one only have 2 cases here. Okay, this gives me 0 if absolute r is less than 1. Otherwise, if I is going to be negative, less than negative, then that does not exist. Okay, so limit doesn't exist. If I is less than -1, and this goes to positive infinity if I is greater than or equal. Okay, got it? Yeah, when I is greater than or equal to 1, you need to do like a 2 square, 2 cubic, let's get larger. So we can still say it doesn't exist, but we can also say that's infinity, the limit is infinity. So only when the absolute I is less than 1, this has a limit, finite limit, and the limit is going to be 0. Using that fact, you can see, right? You can see the numerator, the above, the above numerator has a limit of 1 if I is less than or equal to 1. So then we conclude that this is a 1 minus r, and this approaches a over 1 minus r if absolute I is less than 1. Okay, so this indeed has a finite limit because the second term after the n plus 1 approaches 0 when absolute I is less than 1. Okay, so we can say that we can write it's going to be a over 1 minus r, and that equal. Okay, because the left hand side is viewed as the limit of the finite sum. Okay. So how do I apply that? Okay, we can have a simple application. Look at the problem. Remember in the middle school, maybe elementary school, you already learned this notation, 0.2 bar, right? This means 0.222. So we already have some kind of concept at the limit. Let's go to infinity. Okay, infinity many digits, but it's hard to understand when you're in the middle school elements. Okay, so what does it mean infinity digits after the decimal point? Right? So, but this is a number. Well, how come it's a number, right? And so this is viewed as a limit. Okay, as a limit when n approaches infinity, 0.222 finite many, right? Right, it's finite state. You get a sequence of numbers. Okay, sequence of numbers. The nth term is going to be this number with the n2. Okay, but this one is going to be viewed as 0.2 plus 0.02 plus 0.002 all the way to, okay, you have n, right? So you get series. Okay, it's going to be a series. Okay, so this series is going to be 0. No, it's going to be yeah, you can write 0.2, right? If you express in the above form, that is going to be yeah, 0.2 plus 0.2 times 10 to the negative 1, 0.2 times 10 to the negative 2, and 0.2 times 10 to the negative n, I think. If you have not negative n minus 1, okay, plus 1. Yeah. So you have how many n terms, right? So that means you can also express, well, I don't like this expression. I'm changing. I prefer use digits, integers. I'm going to express in the form. Okay, 2 plus 2 times 10 to the negative. Yeah, this is a 2 times negative. Okay. Let's use a fraction. Okay. 2 over 10. 2 over 10 squared. 2 over 10 cubed. Okay, 2 over 10 to the nth power. All right, so you take 2 over 10 out. So you get the 1 plus 1 over 10, right? And the 1 over 10 minus 1. Okay. So this part, okay, and has a limit. The limit is 1, okay? As first of all, you combine them, we repeated that, right? And then the 1 minus 1 over 10. Okay, can combine all the terms together. then clearly the numerator is going to be 1, the limit of the numerator. The denominator is 1. So after canceled out, it's 2 over 9. Okay? So we were told that by teacher. Okay, 0.2 bar is going to be 2 over 9. Okay, similarly, like a 0.3 bar is going to be 3 over 9. Okay, so in this case, it is going to be 1 over 3. Okay, now how about 0.31 bar? So that's going to be 0.313131. Okay, this also can be viewed as a series. Okay, this can be viewed as a series. It's going to be 0.31 plus 0.0031, right? It's a series. Yeah. The first term will be 31 over 10 squared. The third one, the 31 over 10 to the fourth power squared, and the square and the square. Okay, 10 to the square and nothing is square, like that. This is a cube. Okay, to 10 to 6, and so on. So you will get, if you take 31 10 square out, you will get 1 plus 10 square and 10 square and then square. Okay, so your the I is going to be 1 over 1 10 square, it's 100. 1 over 1 is 1 over 100. So this is supposed to be just 1 over 1 minus R. Okay, this whole term. So it's going to be 31 10 square 1 minus 1 over 10 square. So my answer will be, after simplifying, is 99. 31 over 99. Okay, so we were also told that if we have 2 digits repeated, and that's 2 digits over 99. Okay, so now we see the proof that why this is true. All right, so let me repeat again. This infinite sum is going to be 1 over 1 minus R if I's absolute value is less than 1. Okay. It's convergent to that. All right, so let's take a look at the problem, the next problem. Now, how do we find this? This is also geometric series. Okay, you can express it in order to prove whether it's convergent or divergent. Right, we have to look at carefully. So if you are able to express in this form, okay, then this is going to be A over 1 minus R if I is 1, right? Absolutely, I is 1. Then you can simply use that formula. So, but this is n. N is start from 1, not from 0. Okay, you can change the index if you want. Okay? So, if n minus 1 is going to be k, so when n equals 1, k is equals 0. Okay, so this can be also written as k equals 0, 3 to the power k, e to the k plus 1. Okay, you can change that if you want to use that formula. Okay, directly. Then you will see the e times e over 3 to the power k. Okay, so this is very similar to the above form. A is going to be e. Okay, and the 1 minus e over 3. Okay, because e over 3 is less than 1. That's why you can apply the formula. E over 3 is less than 1. All right, so the answer will be 3e 3 minus over 3 minus. Now, yeah, just apply the formula. But be careful, the index must be start from 0. Okay, if you want to apply that formula. Otherwise, you solve the problem using this formula, the finite formula, right? So n, that's 1 minus n plus 1. Then you decide whether, then you take the limit, whether, to see when it's convergent by divergent. Right? Let's try next problem. It's n starting from 1. Okay, let's choose this one. So this is going to be 2 to the n is x to the n. Okay, how about like this? Right. So we can, sometimes they put in it, like x to the n minus 1, right? But just look at this, right? According to the definition, this is going to be the limit as m approaches infinity. Right? So what is that term? You can express it n starts from 1, right? N starts from 1 to the m. You can express it in the form like this. Okay? Okay. So in order to apply the above formula, you have to begin with a 1. But this time, you begin with r. So you can take 1 out, 1 term out. Okay? Then you will get the first term is still here. The second term will be negative x over 2, and so on. The last term will be x over negative x over 2 to the m minus 1 power. Okay? So combine them, you get 1 minus negative x over 2 to the n power, 1 minus negative x over 2. All right, so the question is when this one has a limit. Only when the absolute value of negative x over 2 is less than 1. So this is going to be negative x over 2, 1 over 1 minus. Okay, if this is less than 1. Okay, only when this is less than 1, then this has a limit, finite limit. Okay, so after you simplify it, it's going to be negative x over 2 and the 1 plus x over 2. Okay, and you can also modify this to be negative x over 2 plus x. And if x is less than 2. Okay, so if x is less than 2, the above series is converging to above series is equal to negative x over 2 plus x. Okay, then the final sum is converging to this number. Okay. Now let's look at other problems. Okay, assuming, consider this series. N start from capital N, n times n plus 1. Okay, any number. Capital N could be 3, 4, 5. So when you write down the details, is you begin with this number. And have infinite many terms. Okay? And this is a limit, right? If we add this many terms together, do we get a finite sum? In other words, what is the limit of this one when m approaches infinity, right? By definition, this is going to be the first term is m plus 1, right? And let's write down the second term, and also the last term. The last term is m plus 1. Okay, but how can I tell whether this one has finite sum? As you see that this chapter is quite different from the other chapter. It requires some mathematical skill to do some analysis of expressions. Okay, that's why it's challenging to some students. Okay, and the winter is coming, so less students will show up in the class. Maybe someday when you come in, you are the only person. I'm not going to push everybody. I just trust them. They find some online lectures to watch it. Okay. Otherwise, the test score will be bad, worse than the previous one. Okay, that's fully up to you. If you want to get a degree in engineering, you have to keep your GPA high enough. Otherwise, they kick you out. They will not accept you. Some students have not been in the program yet. Okay, I met the chair of the mechanical engineering department. Okay, and he told me at the very beginning that I admit like 100 students, the freshman at the minute, but one third of students will drop and eventually have to switch to the other area because of calculus. But he cannot force us to change the course for that. Okay, that's the reality. Okay. All right, so we have to think about this, right? To solve. So what we did, the trick is here, you decompose this every term into two parts. Okay. After you decompose it, and you will see, and then put them in a line. When you see that, you regroup them, and this will be all canceled out. So what is left is just only the first term and the last term. Then this is obvious. This approaches 1 over n as m approaches infinity. Then I can say that all right, so the answer is just 1 over n. Very interesting. So only it's larger than the first term, of course. Okay. Yeah, I would be surprised, if we begin with like say sometimes you get stranger problem, like begin with 2019 and 2020 and add them to get 2020 times 2021 and goes to infinity, right? And what is the sum? That's the sum is 2019, 1 over 2019, right? Yeah. Okay, let me ask you to do this problem. Think about it. Natural log of n over n plus 1, that's the general term, nth term. And whether this series is convergent. If it's convergent, what is the sum? Okay. So if you write down the details, you get natural log of 1 over 2 plus natural log of 2 over 3 plus natural log of 3 over 4, and keep it going. Right? If you add all those terms together, this is the limit case, right? This is actually the limit of m approaches infinity of those terms. How many terms here? The last term will be m over m plus 1. Okay, so you let m go to infinity, and what is limit? Does the limit approaches finite number? Okay, think about this. That just depends on your mathematical skill you have so far. Okay. Yes, which one that? Okay. So if you are watching my video, okay, you're more serious than other students. Okay, less serious than those students who come to my classroom. Okay, please do this problem. Okay, finish it within 1 minute. If you always think that this is a piece of cake, then you don't need to come to my classroom. You can stay in your bedroom. It's very warm. Just send the email to me. You're okay. Okay, you're fine. So any of you here, give me a clue. Nobody? You have idea? Hmm? You cancel lots of terms in the middle, and it's divergent or convergent. You can LN A plus LN B is LN A times B. So convergent to what? I think the answer is LN 0. Okay, let's see whether it's convergent. Okay, so the first term is ln1 minus ln2 plus ln2 minus ln3, and keep it going. Okay, all the terms cancel in the middle. You agree? So the answer. So after you simplify, you will get ln1 minus ln m plus 1. Do you think it's convergent to 0? Do you understand the nature log? The first term is 0, right? The second term, nature log of m plus 1. Nature log of m plus 1 approaches in net positive infinity. So it's negative sign, so the answer is negative infinity, okay? So it's divergent. Right. Now, there's probably there is an yeah, this is a say, then each term, okay, each term, the nth term approaches nature log of 1. It's going to be 0. Okay, each term approaches 0. So you are adding a smaller term to the sum. Okay, but does not mean the final sum, the final result. Because limited case is the final. Okay, you still get more, right? Every time you increase some number a little bit, okay, but you add it some together. It's not like just increase it. Even every time you add a little bit, but the sum could be still infinite. Okay, a typical example is the so-called harmonic series. Right? Let's look at the series. It's 1 over n. So it's going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and keep going. So every term approaches 0, but does not approaches 0 too slow. So this is not an easy problem. Okay, we want to know whether this is a finite. Right? Okay. In fact, Yeah. No, you have to look at this. You look at this, the limit, right? It's gonna be sigma m n from 1 to n, right? So you want to make sure this is defined. This convergence, it's increasing, right? So this Sm, which is called the finite sum, okay? This you got a new sequence, but this sequence is increasing. But can you get up bound? If you can get up bound, it has finite limit. It's increasing as m increases, okay, goes to infinity. It just get more, add more number and numbers. So does Sm has upper bound? Okay. Well, in the book there's a proof. Okay, page 753. It says that if you look at the special one, when m equals 2 to the power k, right? So that's going to be 2 to the power k when n equals 1. So you can show that. Let me write down all the terms here. You can show that it's greater than 1 plus k over 2. Right? So that we cannot find the upper bound. We at least get a lower bound. And this is a pretty technique. Yeah. We get a lower bound, and lower bound increases as k increases. Okay, so that goes to infinity as k goes to infinity. So that means m equals 2 to the power k. So that indicates, okay, the limit as m approaches infinity, as m is positive. Okay, so this harmonic series is divergent, right? It is divergent. We can prove that in a different way later. It is divergent. Okay. Next class, I'm going to show you how to show this much easy way, not very technical. Okay, easy way to prove this is divergent using so-called integral test. Okay. Right. Now I'm going to give you some idea to check whether series is convergent, whether series is divergent. So that's an easy way to check. Okay, but not always useful. Cannot be checked whether this series is divergent. Okay, because the nth term approaches 0. But let me let me talk about the test for divergence. Okay. Test for divergence. It says that if this series n is convergent, well, when you say divergent, why is convergent? Then the limit as n approaches infinity, n must be 0. Okay. So what does that mean? If you have a series, it's convergent, then the nth term must approach 0. Okay. Why it's called test for divergence? Because when you find out the nth term does not approach 0, then it's divergent. But you cannot use that to prove the series is convergent. If conversely, it's not true. Okay, so if the nth term approaches 0, but you cannot conclude the series is convergent. Okay, so this is let me draw. Is convergent implies the limit of n equals 0. Okay, let's look. But conversely, it's not always true. Example is as a counterexample is the geometric series, as the harmonic series. Okay, example. Okay, sigma n from 1 to n, right? This is divergent. but limit of n approaches infinity, when of n is still 0. So when the nth term approaches 0, you don't get the series is not divergent, but the converse is not true. Okay. All right. So why when the series converges, the nth term must be converging to 0? Convergent to 0. So you can look at, okay, the partial sum. The partial sum, this is m, right? If you look at the partial sum, the next one, you see, you can also add them together, n minus 1. And then the last term is here, right? Right. So that, what that means? That means this is a Sm equals Sm minus 1 plus Am. All right. So if the series converges, okay. So if Sm approaches L, a finite number, right? Then you will see that L equals L plus limit of M, right? And then clearly the limit of M must be 0 because, yeah, right? Then this is 0 because this approaches L, this approaches L, then this term M must be approaching 0. Okay, so that implies this is a necessary condition. Necessary condition is not a sufficient condition. Some statement says that something is true if and only if, then there's sufficient necessary condition. But something is true that implies other things. It's just necessary condition. It's not sufficient. Okay. All right. Take a look at this example. Two n minus 1. Okay. Look at this series. It's complicated series, right? Is it convergent or divergent? Well, you take a look at the nth term. The nth term when n sufficient large, this is going to be 1 divided by numerator and denominator by n. This approaches 1 over 2 as n approaches infinity. So that means the limit n approaching infinity is going to be 1/2. It's not going to be 0. So the series, not as a sequence, okay? Then this series is divergent, okay? Why? By test for divergence, you have to say that. You cannot just say, oh, I see it's divergent. You have to give an argument. Okay, so in this chapter, okay, you will act like a lawyer in the court to prove someone is guilty or not guilty. Okay, you have to provide evidence, and you have to quote the law, which law you're going to apply to this case. That's called complete solution. You are not acting like a jury. Okay, I feel like this guy is guilty, you know. Okay, and my feeling, you know, you cannot say that. Okay, you have to precisely show the evidence, not only, you know, and then you have to quote not only evidence. Not, you cannot let me to tell you based on the evidence you provide to me. This is a convergence. You have to tell me which one you are using. As for divergence, that's enough. Because test divergence says that if it is convergent, the nth term approaches 0. Now the nth term does not approach 0. It's not necessarily convergent, sometimes the nth term does not have a limit, okay? Then still okay. As long as it's not as a limit, as long as the nth term does not approach 0, then the series is divergent. Okay, it's called proof by contradiction. Or if it's convergent, the nth term approaches 0, right? Okay. But the test for divergence cannot be applied to the Harmonica series to prove it's divergent. Okay? Yeah. The test for divergence cannot be applied to prove the divergence of the Harmonica series. So that's a remark you have to think about. It's because it's a sufficient necessary condition. You know, this we have to understand what is called sufficient condition, what is called necessary condition. Okay? The test for divergence cannot be applied to prove the divergence of this series. Why? This series, the nth term approaches 0, but that is the necessary condition of the convergence of series. It's not sufficient. So you cannot conclude the nth term as the series is divergent or convergent. Inconclusive if you use the divergence as a test for divergence. And you have to prove that using different way, okay? Using different tests. Yeah, we're going to learn manual. Okay, you have to if I quote to the right one to prove this series is divergent, or you can prove that directly. Okay, let's like in the book, there's a proof argument using elementary mathematics. Just prove that the partial sum, okay, greater than or equal to like 1 over k over 2 something. Remember, right? So that's a lower bound. Lower bound is getting larger and larger, and then push the partial sum get larger and larger. So the limit will be infinite. Okay. Okay. So now I'm going to ask you to do the following problem. Tell me whether this is a convergent or divergent. Divergent or convergent? Convergent have to prove it, right? Divergent have to prove it. All right. So the nth term, if you look at the nth term, clearly it does not approach 0. All right, that's the reason. So n equals 1 plus 3 to the power n to the power n. It's greater than equals 3 to the power n, right? That's greater than 1 because this is always greater than equal. It actually approaches infinity. If you want to look at the limit, this is going to be positive infinity. It's not going to be 0. Then you can say it. It's better to say it's a series, okay? Because we don't know which one you're talking about. So the series is divergent, okay, by the test for divergence. That's enough. You have to say that, okay? Well, according to the test for divergence. Okay. Okay. The second problem, and another problem is same idea like this. Okay. It looks pretty complicated, right? But clearly, the nth term is not getting small and small because with convergence, the nth term must get smaller and smaller. Okay, when n approaches infinity, because otherwise the sum is getting larger and larger, right? It's obvious. Every time we add a 1 to the previous sum, so you increase the value quickly. So, okay, even the harmonic series, every time you add the 1 of n to the previous sum, even harmonic series divergent. If you add a number if you add a number which is not close to 0, then you can make the sum quickly very large. Okay, so same here. So this is n. N is going to be, if you divide by numerator and denominator by n, so that's what you get. So the limit is going to be 1 as n approaches infinity. So for sufficient large n is almost equal to 1. So every time you just add the 1 to the previous sum, you can imagine how quickly the sum, partial sum, get larger and larger, right? So this implies you can find the limit right now. It's going to be 1. It's not going to be 0. So then you conclude that there's a series, not a sequence, okay? The series is divergent by the test for divergence. Okay. Well, I always see that a couple of students still confused about sequence series when talking about divergence. Okay. That's yeah. Right, I'm going to ask you to do the following. Let me erase this. Right. Right. Now, if I put this problem very late, okay, in section 11.5, maybe you would use a different method to trying to prove this is convergent. Okay. So I'll tell you this is divergent. How do you argue? Okay, so I know this is going to be divergent. Well, how do you see that? Suppose it's convergent, right? Then you look at the nth term. Nth term is supposed to be getting smaller and smaller, right? Nth term. Okay, but you make simple observation. N over n plus 1 approaches 1. Okay. Okay. Right? It approaches 1 as n approaches infinity. So there is a negative sign in front of that sometimes. So it actually goes either plus 1 or negative 1, right? It's just switch. So it does not approach a finite number. Okay? So it depends on sign, plus minus. So that means the limit of n does not exist. It's not approach a finite number. It does not exist. Of course, it's not going to be 0, right? Even does not exist. How can you say the limit is 0? Remember, this is a necessary condition for the convergence of series, right? The necessary condition is not satisfying for the convergence of series, because when series is convergent, the nth term approaches 0, right? So we have to put argument in logic. So then you can say that the series is divergent. If you don't want to quote the test for divergence, but you have to say more words otherwise, okay? You have to say, well, it's a necessary condition for the convergence of series, but necessary condition is not satisfied. Therefore, it's divergent, right? By the test for divergence, okay? Series is divergent. Okay, one more problem. 5 to the n, 3 to the n, plus 4 to the n. Okay. Of course, in this section, you only have two types, right? If you prove something's convergent, you have to most of the time you can even find the sum, okay? This is a divergent. Can you see that? The nth term, just because the nth term does not approach 0, but how do you prove that the nth term does not approach 0? Yeah, so this is the nth term, okay? The limit of nth term is not going to be 0. That's all you needed to verify. So this implies the series is divergent by the test for divergence. That's you have to write. Okay. The question is why the limit does not approach 0. Verify this. Okay. Yes. Yeah, you have to prove the statement. This is the key one for. Okay. No, you have to write. Give a complete sentence. Otherwise, you're not qualified lawyer. You have to express completely. You don't assume everybody knows this stuff already. But if you quote, is this series divergent by test for that? If I don't know what it's called test level, I can look at the book where it is and find it. Oh, that is right. But otherwise, still have no clue if you did not mention test for divergence. Okay. Yeah. Even you prove this is a limit to zero, then you can give more details when this is not equal to zero. You prove that's divergent. It's okay, but you don't need to waste so much time. So there's a section you don't need to prove. You just quote test for divergence. Okay, all you have to verify this one, the limit is not going to be zero. So and why is the limit? Why does not approach zero? I think the numerator is much larger than denominator. That's it. Okay, question is how do you have to prove that it's greater than or equal to some positive number, right? So you can make the denominator large, right? Make the denominator large, you just replace 3 to the n to the 4 to the n. How about this? All right? Yeah, that's the trick. This is the mathematical knowledge, if you this. It's simple, but how do you know that, right? So you make 3 to the n large, then the fraction is smaller. That's it. Okay. So that is going to be 2 times 4 to the n. So that's going to be 1/2, and 5 to the 4 to the n, right? Now 5 over 4 is always greater than or equal to 1. So to the nth power, it's always greater than 1. So that's greater than or equal to 1/2. That's all I needed. It had always greater than or equal to 1 over. Okay. Therefore, n does not approach 0. I don't need to know the exact limit, whether the limit exists or not. I can conclude that n is not going to be 0, the limit, if it exists. If it does not exist, that's fine. Okay. Indeed, the limit exists. It's infinity. Okay. How do you see that? Why it's infinity? Here's another way to look. Okay, if you don't want this, okay. So 5 to the n, 3 to the n plus 4 to the n. I divide the numerator denominator both by 4 to the n. Right? And what I get is a 5 over 4 to the power n, 3 over 4 to the power n plus 1. And it approaches numerator positive infinity. The denominator is 0 plus 1, right? Because 3 over 4 is smaller than 1. To the nth power, you make it smaller and smaller. So the approach is 0. So the numerator approaches infinity. The denominator approaches 1. The quotient approaches infinity. So this is actually the infinity. So you are adding larger term to the final sum. You make this partial sum grew very quick. Of course, it's divergent. Okay. I think that this was a problem on the final exam, previous final exam, because I remember that I made all the final exams the past 7 years for Math 166 for all the sections. So the way we do is I made a private version and send it to all the instructors and make the corrections, suggestions, and modify it, and send it to the secretary that print out 500 copies. Okay, that's what we do. All right, so you see that all you need is to prove the limit is not going to be 0. Maybe it does not exist, maybe infinity, maybe finite, but as long as it's not going to be 0, then you can conclude the series is divergent. So there's difference between sequence and series. Be careful. If we ask you to prove the series is convergent, you only prove the nth term is convergent. That's not enough. Okay. Read the question carefully. There's a difference between series and the sequence. Okay. Okay. Look at this series. Is it convergent or divergent? Okay, this series sometimes I give to you in a different form. It's like that. Okay, it's the same. But if you are given a series like that, it's much harder to see whether it's divergent. Okay, of course later on we're going to learn more tests so we can check that. But if I'm given this in this form, the left side, it'll be much easier to see it's divergent. How? All right, so to prove you see the nth term approaches 0. You cannot use that to prove it's divergent. Okay, so the nth term. Okay, let's look at this is n plus 1. Okay, so you want to see whether this approaches 0 or not, right? First, if it's not approaches 0, then it's divergent. But when you look at this and you use a standard method to change it, look, right? And the numerator is n plus 1 minus n. That's why it's going to be 1 over n plus 1 plus. And unfortunately, this approaches 0 as n approaches 0, right? So that means the limit is indeed approaches 0. What I can say conclusive by the test for divergence. Okay, you cannot use test for divergence to prove it's divergent, because test divergence says that if the limit of n term is not going to be 0, then it's divergent. Now it's 0, so it's possible convergent, possible divergent. Inconclusive. You cannot say it is divergent by the test of divergence. Then you don't get points. Okay, even you say, oh, my answer is correct. You know, your answer, we don't call it an answer, we have a solution. The solution, including your final answer, and all the steps to support the answer. Okay? You have to show your work. So you cannot jump to the conclusion, maybe grader give you a few points out of 10. If you just jump to, you just say it's test for divergence, because when you prove this limit is 0, then some student will look at the student sit next to him. He saw it's divergent. They just say divergent and have no clue why it's divergent. Okay, that's why we cannot give you full credit, even the final answer is divergent. Okay, because you did not give a proof yet. Okay, the evidence you provide is not supporting. Okay, to your conclusion. So we have to go back to the original definition. We have to look at the partial sum. It's called partial sum. Oh, it's still not perfect right on the screen. Yeah, I hope someday they can make a screen like a soft, like a piece of paper, so I can write on. So it's not glass window. I'm pretty sure, yeah, in a few years that will be. Okay, screen would be not like a glass screen. So you can write like a regular tape, feel like tape. Technically, it's not easy, but it should be. Smart boards, really? I never heard of that. Okay, the partial sum. Okay, but it's better than 4 years ago. Now I feel like, yeah, I can write better. The partial sum m and start from 1, right? N plus 1. Okay. So if you, I'm not going to combine it, but if you write down all the details, it's going to be 2 minus square 1, that's the first term, and square 3 minus square 2, the second term. The last term is m plus 1 minus square m. Then you will see all the terms cancelled out. I think this term will be cancelled. So finally, only the term only left, just 2 terms left. And clearly, this partial sum approaches infinity as m approaches infinity. Okay, so that my conclusion is right, it's divergent. Then you say it's divergent, it's because it's not finite. Okay, if it's not finite, then it's divergent. So sometimes you have to go back to the original definition of the convergence of series. Yes.
So if we figured that out before we ever did test.
No, yeah, before you don't need to use the test for divergence. You cannot use it. You can do some extra work. You find out the limit of n equals 0. Okay, but you switch the new idea. Just look at the partial sum. Okay, if you look at the partial sum, and you find the partial sum approaches infinity, then you can even erase the previous part. Okay, yeah, don't put the two solutions contradict each other. Sometimes, yeah, something wrote, let me to choose which one is right. Yeah, cannot do like that. Okay, you have to say, I'm sure. Cannot say, I'm not. Maybe, no. Okay, so this is a divergence. Okay, although every term is getting, the nth term is getting smaller and smaller when n approaches infinity, but add them together, you eventually get infinite sum. Okay. Yeah, we have to gradually understand the infinite sum. We call it infinite sum. It's also called series. Yeah. Okay. You have so many terms together. Okay. So many terms together that I thought there's a problem already. Students in the middle school applying this geometry series. Why it's called it? Because coming from geometry. This is the example problem I want to talk about. It's interesting. It's a unit square, divide into 4, you shatter it. Okay, then you divide into 4, then and keep it doing. Okay, and what this is unit 1 by 1. Okay, unit square. Okay, so what is the area of the shaded region? It's clearly less than 1, but the total area, I mean, it's really needed to know that the limit idea, right? The area of the shaded region is going to be the limit of, is going to be the series. Okay, it's sum of all those areas of small squares, getting small, right? Okay, add them together. Okay, so the total area, if this is area 1, A1, that's A2, A3, so this total area is going to be K from 1 to infinity. Okay, so you add them together. Okay, and it is finite. Okay, it's it actually greater than 1/4 clearly, because the first one is already it's 1/4, right? And the less than, maybe you can find the limit. Okay, so sum infinite terms there. Okay.
But if, you can only go so far at a 1/4.
Yeah, it's hard, but if you zoom in, you can always draw, okay? But according to physics, if it's too tiny, you cannot even draw it, right? It's like the size would be one, less than 1/10⁻26 power in meters. It probably no longer you can draw it. I don't know. Maybe this theory is wrong. Who knows? So that's called science. Many years later, find out what we did before is wrong. It's called Planck constant. I heard about, right? You learn that from general physics. If you take a physics course, yeah, physics tell you, yeah, if the some object is the size is more than 1/10⁻26 meters, you cannot recognize. Okay, no matter you cannot zoom in and draw another little square, okay, because the atoms the size of this is so small, and that's possible. Yeah. Yeah, you can, maybe it's true in some way, something, but from mathematics point of view, you can always go to the, no matter how small it is, you can always find the size, determine the size, okay? We stop here, maybe I'll continue this part, maybe, you can think about it.